B bar and velocity. Oh, yeah, I have to shift it down. Huh? No, things will change. At t equals 0, it will enter here. How the charge particle will move in this magnetic field. So again, the B bar velocity, the force. So it is going to deviate. I have to bring a circle. Some lighter colors. Okay, look at now. This will be the path of charge particle. Sir, how you can predict all these things? Sir, how do a student should get an idea? Okay, well, we have a method. Okay, let's follow that method. Okay, this is the at the moment at A, the force will act here. So definitely looking at this force, where the center of curvature will lie, somewhere inside the magnetic field. Then again pick up one more point. Pick up one more point. Pick up one more point. Pick up several points. Nobody will punish you if you think like this. Nobody will punish you that one. So if you extend all the lines, they will meet at a point, center of a circle. So where the center of circle now? So they're the only method available to predict the center of the circular path. Okay, I think you do get very complicated problems, but the methodology is same. They just stick onto the basics here. What do you mean by center of in circular path, curved path? What do you mean by center of curvature? Where the resultant centripetal force will be directed. The simplest example is what I'm trying to give. Anything will happen to speed of charge particle in magnetic field. It is not going to change. It is not going to change. Then after leaving circular path, anything will happen to charge particle. It's going to continue straight line path. Why do it will come again? Common sense. Path of particle outside the field. Inside the field, curved path. We have asked even such questions, and I don't know, some great thinking brains are there. What they're telling, sir, it will go around. How it is possible? It'll go undeflected, no? Similarly, same thing here. Path of particle outside the field. Now let's write all the possible parameters for the path. And there's a center of curvature at point A, and at point D it will leave. So I'm interested again this beta. Okay, this angle should be alpha. This should be beta. So anything alpha, beta, again they're equal. So again the same conditions. Particle enters at point A with an angle with velocity vector such that the path what happened there will make an angle alpha with the vertical or the boundary of the magnetic field at t equals 0, what is the time spent by the charged particle in magnetic field, and what is the radius of curvature, all the things we are supposed to find out here. Let R be the radius. So first, what is the radius? mv by qb. Then what about the time spent? Total time spent. How much of deflection it will undergo? 2 pi minus 2 alpha. First thing, alpha equal to beta. Okay. Then the time spent is equal to t equal to theta by 2 pi. Theta will be 2 pi minus 2 alpha by 2 pi. Some problem. Okay, this omega actually it is. Further, what is omega? B cube by m. 2 into pi minus alpha. What is this T you should call? Time spent by charged particle in magnetic field. I have to calculate the distance CD. So for that, sine alpha is equal to AP, this distance. Look at this triangle here. Sine alpha equal to AP by, or say PA by AP by AC, will write it. This AC is what? R. So what is AC equal to? AP is equal to R sine alpha. R is what? MV by QB. What about the distance? Again, similar way we can. So the distance AD will be where it will leave the magnetic field at a distance D. So what is the distance? We can calculate that one. So this the distance AD should be equal to 2 times of AP. So 2 MV by QB sine alpha. Okay, no, see the way I think it's really I can bring any best numericals. What we discussed is only positive charge particle. So can I bring negative charge particle? Yes, like this. So many varieties of questions will come. Next, I'll bring gravity. Next, I'll bring viscous force. I'll bring spring force. So all